So, good morning to everyone. So, in the last class, we have seen the various types of signals and classifications of signals and classifications of system. So, in this class, we are going to see about the concept of quantization, the process of converting to discrete time continuous time signal x of n into discrete time signal x amplitude x2 of n is called quantization. So, this is done by the rounding of each sample x of n to the nearest quantization level. So then each sample is xq of n is represented by a finite number of digits using order. So if a signal with the amplitude range r is represented by b plus 1 bit word including single bit sign bit, then the number of values or the quantization levels that can be represented is 2 power b plus 1. The difference between the adjacent levels or quantization step in terms of range of signal, q is equal to range of signal divided by number of quantization level, r is r divided by 2 power b plus 1. With a fixed point representation of a fractional number, if the range of signal x0 plus or minus 1, it is called necessary to scale the signal. The process of quantization is known as given below. The sample value quantization value is described in the picture. So the time axis of the discrete time signal is labeled with the sample number corresponding to different values of a sample number in n, the discrete continuous time amplitude signal shown in the figure. So we can represent the sample values by a sequence. X of n is equal to the given sequence. Let's be a b plus 1 bit ADC is used to represent the above signal with b plus 1. So binary digits 2 power b plus 1 quantization level can be obtained and the input signal can be resolved into one part in 2 power b plus 1. If the input signal has a range of 2 volt, then the quantization step size is q is equal to 2 power 2 plus 2 power b plus 1 is equal to 2 power minus b. So if a b plus 1 signal is 2, the quantization step size is 0.125. Thus the input signal must change almost 0.125 in order to produce a change in output. So it's a sequence x e of n defined as the difference between the quantization value and the actual value. E of n is equal to xq of n minus x of n. So this is a representation of quantization using rounding off. So here the various values of binary representation and rounding off and quantization value and quantization noise we have to find. So what is these are all the example problems about in the part B questions they have they can ask like this: what are the classifications of signals and what are the classifications of system with the example. It's a one type of questions usually asking in university questions, but they have described one type of problem. They have given certain problem and they can check whether that system is linear or not, time invariant or variant, causal and non-causal, stable or unstable. So likewise we have to put the condition basically the condition is correct in the sense they will give a marks if you, even though the problem may be wrong, problem which you are going to work out might be wrong, but if you write the conditions good in the sense they will give a definitely the marks out of 13 out of at least 10 or 11. So likewise we are having the various problems. So in this problem, what is the causality and stability of the system derive the necessary sufficient condition for an impulse response of the system. So causality, so the derivation of causality using the convolution sum y of n is equal to summation k is equal to infinity h of k x of n minus k. So h of k x of n minus k plus h of k x of n minus k. So likewise we are having the equations. Output depends on the past and present values of the input. K less than or is equal to 0. If k less than greater than is equal to 0, k less than of the output depends on the future values of the input. So therefore the causal system whose output does not depends on the future values of the input, the limits of the summation changes. So y of n is equal to summation k is equal to 0 infinitive x of k h of k x of n minus k h of k is equal to 0, k less than is equal to 0. An LTI system is causal if only if impulse response is 0. The limit of its convolution sum can be modified according to the type of sequence and system. So for the causal system, the impulse response h of n is h of n is equal to 0, n less than is equal to 0. Therefore, the limit of a convolution sum is y of n is equal to summation infinity k is equal to minus infinity x of k h of n minus k. So likewise, we are having the stability conditions, the derivation. If some bounded input is equal to bounded output is called that stability condition, otherwise unstability conditions. Y of n is equal to summation k is equal to minus infinity plus infinity h of k x of n minus k. So likewise we are having the problems. So up to this we have completed the example problems and the sampling and the quantization. In the next class we will see some of the example problems. Thank you.